Hello everybody, and welcome to the top of page 96 in the workbook. We are about to make a new definition. And just to kind of recall what we've done so far in this chapter, the first big definition that we had is the idea of an integral domain. Okay, and what we are about to define is the idea of a field, okay, which is also a special type of a ring. If we read this definition together, it tells us that a field is a commutative ring with unity in which every non-zero element is a unit. Okay, remember what that means again. That's just saying that to be a field, we need every non-zero element to have an inverse relative to multiplication. Okay, and I'd like to start by giving you just one example of a field, just so you can get a feel for what this is. We're going to turn the pages, okay, and just put this on a blank sheet of paper here. So I claim that the set of all real numbers is a field. Okay, and I'm talking about just ordinary multiplication and addition, okay, of real numbers here. Why is that a field? Well, let's think about the properties that it has to have. According to the definition on the previous page, it needs to be a commutative ring, okay, which it is, because multiplication is commutative. It has to have a unity element, okay, and our unity element is 1. 1 is a real number. And the other property it has to have is that every non-zero element is a unit. Okay, so that means that if I give you any non-zero real number, you should be able to find an inverse for it. Okay, so let's just play a little bit here. So if I give you 3, for example, it should be possible to multiply 3 by something that would give us 1 back. Okay, that's what it means to have an inverse under multiplication. What is the magic number here? Well, it's 1 over 3. 3 times a third gives us 1. And 1 over 3 is a real number. Okay, so it's a valid inverse for 3 in this ring. Okay, what if we took something a little bit crazier like the square root of 2? Can we multiply that by something that would give us 1? How about 1 over the square root of 2? That's also a valid real number. Okay, so we've shown that square root of 2 has an inverse relative to multiplication. And you can convince yourself that you can do this with any real number, okay, that's not 0, and come up with something that you multiply it by to give you 1. Okay, so the key then here, we're kind of convincing ourselves that every non-zero real number is a unit. Okay, it has an inverse relative to multiplication in this ring of real numbers. Okay, so R is a field. All right, now back to the definition itself. We're going to play a little bit more, see what other properties we might be able to come up with for a field. One big one is the following. I claim that fields cannot contain zero divisors. Okay, now I want to give you just a brief argument to show that, and I'm going to just write it out. We may have to think a little bit about why this shows that we have no zero divisors. Okay, here goes. So let's suppose that we know that AB is equal to 0. Okay, product of two things in our field equals 0, and that A is not equal to 0. Okay, well, if that's true, then A has to have an inverse relative to multiplication, because in a field, every non-zero element has an inverse. Okay, so that means that we can take this equation and left multiply it by the inverse of A, okay, which we know has to exist. And notice what happens as a result of all of that. Okay, so A inverse times A, that's just going to give us the identity, or the unity element. And they're going to cancel, and we're just going to get B on the left-hand side. And over on the right-hand side, A inverse times 0 is just 0. Okay, and just as kind of a comment, there wasn't anything special about A. We could have also started with the assumption that AB equals 0 and B is not equal to 0, and gone through a similar argument and come up with the fact that A would have to be 0. Okay, so what is it that we've proven here? Well, basically, we've proven that in a field, if you have a times b and you get 0, then at least one of the a or the b has to be 0. It's impossible for both the a and the b to be non-zero. Okay, and if you think about that, that statement exactly rules out the possibility that we have zero divisors. Okay, and so that observation leads us to a very important second observation, and that is that every field is an integral domain. Okay, do you believe that? Okay, let's go down the properties. What three properties does an integral domain have to have? Well, it's got to be a commutative ring, it's got to have a unity, and it's not allowed to have zero divisors. That's what we just gave a little argument of up here. So fields have all three of those properties. Okay, and so what we're in the position to do now, space is a little bit tight here, but we can draw kind of a nice diagram to illustrate how some of our definitions relate to each other so far. Okay, so what I'm going to do is to draw a Venn diagram here. And it turns out that fields are kind of the most specific type of ring that we've talked about so far. Okay, every field is an integral domain, so the set of integral domains would be a little bit bigger than that. Okay, and if you go a little bit bigger still, every integral domain is a commutative ring. Okay, and then even bigger than that, we could talk about the set of all rings. Okay, so there's kind of a nice sort of picture description of how some of these various types of rings relate to each other. Okay, and what you could do maybe is just a nice exercise to explore a little bit here is maybe see if you can answer this question. Okay, if you go back to example 1, I believe that was the one that was on pages 98 and 99, you could ask yourself, which of the rings are fields on that list? Okay, in exercise 1. Okay, I think that was page 98 and 99. You can check it. I'm talking about the exercise where you kind of had a big long list of rings and had to fill in properties about them. Okay, and then maybe one other thing you might do is to see if you can find an example of a ring in each zone of this Venn diagram. So for example, could you find an example of a ring that lives there in the set of all fields? We kind of already found an example. R, the set of real numbers, was a field. And then you could ask yourself, could you find a ring that lives here in our Venn diagram? That would be an integral domain that's not a field. Okay, can you find an example like that? And then what about a commutative ring that's not an integral domain, and so on. Just kind of see if you can find an example of each type. That might be a way to just build some insight into these definitions that we're talking about.